All right, we have drawn the mechanism together. Now let's take a look at the real deal in here. All right. So if you have a symmetrical ketone, okay, add a peroxy acid like MCPPA, so you're gonna get this intermediate, right? And the migratory group could be one of these two methyl. So let's say if I take methyl on the right, migrate up to the oxygen, right, you're gonna get this product, right? If I use the other methyl group, migrate up to the red oxygen, I'm going to get the same product, nothing different. Well, we use symmetrical ketone. The fun part's right here. If you start with a symmetrical ketone, well, here's the fun part. Well, what group's gonna migrate? Is it methyl? You get that right there. So methyl go up to the red oxygen, right? Or the phenyl. Phenyl can go up to, can migrate up to the red oxygen. Well, the question is, which group migrates? Well, let's do some experiment together. All right. So I'm gonna walk you through all the experiments that people have done in the past, and I'll have you guess which group to migrate. Then you can predict it. Okay. All right. Let's say if I have acetophenone, so we get either methyl or phenyl. Adding a peroxy acid. This one we use trifluoroacetic acid. All right. So you have two options: either phenyl migrate to oxygen, or the methyl migrate to oxygen. All right. We found that if you use acetophenone, 90% 90% yield, and all the yield phenyl migrate. Looks like phenyl migrates better, tends to migrate better or faster than the methyl migrates. Well, we're gonna go further. Use the new compound. So we use change methyl to an ethyl group. I use the same peroxy acid. Right. So you got two options again: phenyl migrate on the left side or ethyl migrate on the right side. Okay. We found out that the mostly phenyl migrate, 87%. That's a major product. Now the next one, we have an isopropyl. Add the same peroxy acid. The migratory group is, take a look at the percent ratio. 33% phenyl migrate, 63% isopropyl migrate. Looks like if the alkyl group is more strictly hindered, they'll move better, they'll migrate better than the phenyl ring. You know? Try one more time. You can guess now. All right, third butyl group, take a look. So phenyl migrate or the third butyl migrate. Okay, we found that most of it is tertiary. Can you come up with the tendency of migration? I'm sure you can. Here we go. Tertiary better than secondary, better than phenyl, primary, and methyl. All right. Hydrogen is not on here, but hydrogen is actually the best one. All right. That's the. If you ask me why, well, it's difficult to explain. No one actually knows what's going on here, but there are a few theories that they propose. I'll give you one of them. Okay, this theory cannot explain why hydrogen migrate better than the rest, but at least they give you something to think about. Okay, take a look at this one. So this is a hypothesis why what group will migrate. All right, if you look at this compound, so we have methyl and isopropyl. Okay, so you get two options: either isopropyl migrate, look like that. All right. So in this case, take a look at the transition state. The transition state is about to form a positively charge on the migratory group. This carbon is migrating. Right? So there's a positive charge right there. Compared to if methyl migrate, so I have methyl migrate to the red oxygen, the positive charge will be on the methyl. And you guys know who stabilize positive charge better? Well, hyperconjugation, of course. The more alkyl groups, so in this case, going to be secondary, and the secondary goes faster at a faster rate. Okay, cannot explain why hydrogen migrate better. That's another theory, but we're not going to get to the detail. It's steric hindrance. Okay, but it's not the steric hindrance of the migratory group. It's something like yeah, we're not getting into the detail. Okay, anyway, so let's predict the product together. All right, so this is how we do it. We have phenyl and we have versus hydrogen. Hydrogen the best. All right, so we're going to insert oxygen at MCPPA Baeyer-Villiger reaction. Oxygen right there, you get carboxylic acid. Okay, all right, let's do the second one together. Let's see what we got. So the carbonyl right here. So we got secondary versus tertiary, and of course tertiary migrates faster. So we go that one right there. Put oxygen between carbonyl and tertiary carbon. Okay. The next one, so look at the peroxide acid is a weak one, so hydrogen peroxide, but it works. This one works. Carbonyls right here. So we have tertiary versus primary. Of course, tertiary win, right? So insert oxygen right there. And lastly, all right, don't let the structure confuses you. It's not that confusing. So we got a secondary plus allylic right here, and primary right there. Okay, so we're gonna insert oxygen right here. Here we go. Ta-da! All right. Okay. All right. Before we go, so one more. This is an application of Baeyer-Villiger oxidation. Let's see what we do. Start out with L-tyrosine, making L-dopa, which is a pre-drug for treat Parkinson's disease. Okay, and let's see what happened. If you want to do this reaction, it looks like you just have to do hydroxylation right there. Put one more OH group in there. Well, what we learned so far, all the reaction we have learned from the previous chapter, all the aromatic reaction. How do we put an OH on a benzene ring? Well, you probably think about like a benzene reaction. You probably think about elimination addition reaction, right? Or the benzene reaction, or nucleophilic aromatic substitution. But those require a lot of heat, right? And anything in the molecules that not as stable as benzene, like this functional group right here, cannot withstand that heat. Can't do that, right? What about electrophilic aromatic substitution? Anything here allows you to add an OH group? No reaction. None of this reaction here allow you to add an OH group at all, right? And you have to add an OH plus. So we want the the benzene to attack at all the position from there, right? And the OH plus, what do you know about stability of OH plus? No, it's not real. It's synthetically impossible to make it, right? Well, how do we make L-dopa from L-tyrosine then? Take a look at this brilliant reaction, the synthetic plan. Okay, so start out with L-tyrosine, do Friedel-Crafts acylation. So put this is going to go on auto right here, all right? And then Baeyer-Villiger oxidation. Let's take a look. The carbonyls right here. Okay, so we have a methyl competed phenyl, who tends to migrate better. The phenyl, so you put oxygen right there. That's your oxygen, right? And next one is acid catalyzed hydrolysis of ester. You haven't learned it yet, but you learn it in the next chapter. Okay, this one, so acetic acid comes out, and you get L-dopa. Basically, this reaction scheme, this synthetic plan will synthetically impossible species like hydroxide with the, not even hydroxide, what is it called? I don't even know what we call it. Hydroxide with a positive charge as an acetyl group. It's amazing. How do you put this together? These two are synthetically equivalent in this synthetic plan. It's amazing. How could you even thought about that, right? But it's one way that we make L-dopa from L-tyrosine. Okay. All right, next slide, next video, we're gonna talk about synthesis, using all reactions you learned in this chapter and maybe previous one to do some synthesis in there. All right, let's move on.